Hello. Um, so today I'll be taking a slightly different approach due to some time constraints. I'll be going through tons of examples, tons of problems, and I spent like 5 minutes on each problem, supposed to. Even then, I don't think I will be able to cover everything. But I hope the audio and stuff are coming in fine. I'm not gonna care. I got bigger fish to fry. So we're gonna breeze through a lot of problems, and I should have done this stream long ago, but I'm just doing it now because I don't wanna. I just want to warm up myself talking to myself prior to doing it in a way that matters. So let's go. Let's start sharing the screen. So we got a new drawing board. Okay, so this is a problem that I think we covered previously. It's a two-pointer problem. So the difference between two-pointer and sliding window problem, what is that? So a pair, when they say a pair, you only need two numbers. In that case, you could just use two numbers without a sliding window. We don't need the window because we're only looking for exactly two numbers. But when we do look for so here we look, this is actually a binary search provided. So okay, yeah, all right, this is a good one. So provided the array is sorted. Is it a sorted array? Sorted numbers. So if it's sorted, you can use binary search. You start with left. You can call this left and right, and then compute. And if it's left is larger or smaller, you just move the pointer until the sum of both pointers equals to the target pair, and then we found it. It sounds easy, right? But try implementing it. I'm sure you'll lose some of your joy. Alright, so that's that. You don't need to draw a lot. Remove duplicates. That's the second one. Another caveat or disclaimer that I might take this video down because it contains things that might be subject to copyright, and as this content is from a paid course. So yeah. Okay, what is the problem? Remove duplicates. Given an array of sorted number, remove all duplicates from me. No, use extra space. Okay, so this would involve two pointers as well. So you'll just use two pointers and move the pointer, keep track of the different number, or right to right. So and then there'll be a current pointer, and you write if it's not different from the previous value. How would that work? Okay, you've got two pointers, 1 2 3 4 5 6. Okay, start with this, move, and then the next pointer here, different. Okay, start pointer, and then right pointer is 3, and then you read 3, and then if it's different from previous, you write 3 and move on to next, and then the current pointer moves to here, and then this pointer is the same, so we don't increment the left pointer. Move on to the next one. It's same as the current pointer. Move on to the next one. So this pointer is not same as current pointer. Okay, no. Yeah, this is. We need two pointers. Next non-duplicate and next. And then move the next to non-duplicate. Next non-duplicate into next, and then okay, so this is a duplicate, and this is next, and then next non-duplicate. So basically where to write. So this is the pointer you keep to where to write, and then you move to next, Is it already exists? Yes. So you move to next one. Is it already so 6, the 6 already exists here? Yes. So you write to 9. I don't know, I'm not following anymore. So next non-duplicate equals to 1. I equals to 1. Well, and then okay. Yeah, basically just move the pointer, and we compare with next non-duplicate minus 1 with current. Okay, so we could actually use 3 pointers here, but instead what they're doing here is just this is highly optimized code. Which is why you would ideally wouldn't arrive to this code when you first tackle this problem. It's optimized, so you don't expect. So you probably have 3 pointers, but the 3 pointers can be reduced to 2 pointers, as we're seeing here. And the invariance, the things that invariance that we can exploit is that the 2 pointers on the left are usually off by 1. So here we can say writing pointer, and then the last non-duplicate, and then where to write. So it's the last, and then usually when last non-duplicate, and then this is next pointer, so you'll usually line to the next pointer. So you can see this is the last, and this is where we write. This is the last, and this is where we write in the next case. It sounds easy, but I don't think I will be able to do this in time. Okay, how's my stream coming along so far? If you're looking at this, this is a mistake. I wanted to buy a headset with a good decent mic, but I got a horrible one due to my optimization techniques. So that's unrelated. Oh wait, and the similar code. So remember, I remove all instances of key in place and return new. So we can use a hash table. They are using hash table. Given a unsorted number of array and a target key, remove all instances of key in place, or to basically just really remove one particular number. So here we would do keep a pointer, next element, keep a pointer, and then move along another pointer, and as long as the pointer is not 3, we write. As long as the pointer is not the key, we write to the next available element. Okay, seems is there a reason why they're using +1 instead of 4 in range? I don't think so. Yeah, I don't think so. Okay, it's okay if you don't fully comprehend this. Eventually, you know what? Let's go through this problem. Do we have time? We don't have time, of course. Okay. So this is the numbers. This is the number, so maybe you can maximize it. Okay. say 7 and 5. Okay, so let's say we start with this pointer, and then I hope you can see my screen. Yeah, okay. Start with this, and then another pointer, and okay, this is the writer, and then we loop, we move to E. No, maybe this is C, and okay, let's this is writer, and this is current, or maybe this is writer, this is current. Yeah, I'm stuck. Alright, never mind. So one of the invariants that we discovered was just keep track of the last sorted. So last, okay, let's say this, let's call this L, and then this is current. Okay, this is current, this is last, and if current minus 1 not equals to array current, if current minus 1, so the previous number is not same as the current number, we write a L plus 1 equals to A equals to C. So we write the current number. So here then the tree, so since this is equal C minus 1, C is, okay, let's do 0, 1, 2, 3, 4, 5, 6. So C minus C is at 2, 2 minus 1 is 1, that's 3, and then C is 3, it's the same, it will skip. So moving on to next iteration, C will be here, C, and then this will be the same, it will move on to the next one. 4 will look for the previous one, it's not the same. What we'll do is what it will do is if it's not the same, so it will L plus 1, it will write 6 to here. Let's say 6, it will write 6 here because this is the L is 1, L plus 1 is 2, we will write it to here. Then the L changes, and then L equals to L plus 1, so increment, so move the L to here, and then C moves to here. Previous number is not the same, or we do L plus 1, so we write 9 here, then L moves 1 to the right, then we move to the next one, is equals to the previous one, so we don't do anything, so we'll get L here. So the way we return is L, where we just return the pointer to L. So that would work. Okay, that would work. At least get some idea of how to implement this. And I think the audio is coming in fine. If it's not, I apologize. I just wanted to get into the pace of me explaining things. That's all. It's not meant for anyone, and I get nervous, very tensed. So doing this kind of helps me and makes me a bit cocky. That's good usually. Okay, so that's the second one. Let's move on to the next. Oh my god, we're running out of time. Okay, maybe we'll just go for easy ones. So what is the problem? Squaring a sorted array. What the fuck? Given a sorted array, create a new array containing squares of all numbers of input array. You can just wait. Given a sorted array, create a new array containing squares of all numbers in the input array. Wait. So 2 to the power of -2 is 0. Okay, so that's the trick. So that's the tricky part. Negative numbers are the tricky part. An easy approach would be find the negative number of non-verse, and then after that so we'll have 2 pointers, and then you move to the left, one move to the right. Okay, well, left and right. Squares, we just initialize an empty array, highest square index. What does this have to do with anything? It's 4. Okay, yeah, I get what you mean. We'll get +4, and then that has to be on the other side. So this is a tricky question. For mention, we'll do something like pointer 1 goes to this, but since the number what the answer gives. Since the number alternate approach will be to use 2 pointers, starting at both ends of an array. Oh, this is smart. So you start with 2 pointers, left and right, and then you square both numbers and see which one is larger and add that to the. Okay, well, left is less than right. Okay, left square, right square, and then if left larger than that, so the index, you just write the left square and then move the left square to the right. Oh, this is amazing. Yeah, today I learned. Okay, let's move on. I hope it makes sense. So let's say, do I have to explain this? So we have 2 arrays. We have 2 pointer here, and then so let's say this is left, and then this is right. Then we constantly keep a square of both these two values, and then if left is larger than right. Okay, so ideally what we keep an empty array, and then whichever is larger we write it first. So if L is larger, we write L. If R is larger, we write R, and then so on until, and then we move L to this way and move right to this way, as long as this is not left and right are not the same. Is that logic? I mean, that's an edge case that you probably can figure out by tracing through, but that's the essential idea here, which is quite interesting. I wouldn't have figured this out myself without some help. Okay, here comes the triplets. Jesus. Given an array of unsorted numbers, find all unique triplets that add up to 0. This sounds like a dynamic programming. These are also 2 pointers patterns similar to the target pair. Some a couple of differences. Okay, I don't know what the fuck they're saying. Okay, 2 pointers target pair. Some a different approaches. The input array is now sorted. Instead of a pair, we need to find triplets. To follow similar approach, first we need to sort it. Okay, so this is something interesting. Consider sorting the array, but when do you know when to sort? That's important. Let's trace blah blah blah. I think I'm running out of time. Another difference is that we need to know all unique triplets, so they can be duplicates or the orders. Just keep in mind since we all belong to. So this is pretty involved. It's a medium question. Yeah, no, I'm not. Maybe we can come back to that later. Triplets are ridiculous. Maybe we can do. They can do it O log n. If they want triplets, I would put O(n) cube. That's optimized. And then so yay, linked list. Let's go to the next one. This is the linked list, and we use fast and slow pointers. Given a linked list of write a function to determine there's a cycle. So the idea behind it is keep a pointer at the head, and then every time you jump 2 pointers, and then keep going on. And if there's a cycle, eventually the slow pointer and the fast pointer will meet up. Right? So this is the code. So cycle is the fast pointer which handles linked list. For slow pointer, well, there's no cycle. Okay, so slow pointer will never be able to catch up. It is slow pointer. There's no cycle to linked list. And another thing that you can do is like if it's jumping by 2 steps, so by the time the fast pointer ends up at the end, you will probably the slow pointer will be at the middle of the list here. Move by 1, you move here, fast pointer moves by 2, and you move by 1. Fast pointer moves by 2 again. But then it's already low. I don't think it's making lots. Okay, so slow fast starts with here. So this is a better diagram. Start with the same pointer. Slow pointer moves by 1, fast pointer moves by 2. And I keep on doing this by 2. And then fast pointer jumps 1, 2. It ends up at the same path, and slow pointer moves by 1. And then jumps another 2, and we meet. So that's low. So the algorithm will look like. Okay, this logic is kind of hard to come by. So slow, fast, head. Start with head. Fast is not known, and fast next is not known. So both of them. Yeah, so this was the edge case. I was thinking about, like, what if in this case, if we jump, if the fast point is here, we can't jump to the next one because this one is no. So that while loop catches that condition, right? So if fast equals slow, return to, yeah, from the cycle. That's a good one. Given a singly linked list that contains a cycle, write a function, find the starting node of the cycle. Okay, this is similar as cycle, but cycles, you have to find the cycle start. It is similar to the previous one. It's just that when the start and slow pointer is the same, we return the number. Yeah, this, yeah, when slow, we just suddenly identify as follow the mentioned step. Instead of returning true or false, okay, I think I'm missing something here. I think maybe I'm not understanding the question. Given a head of the list that contains a cycle, write a function to find starting node of the cycle. Wouldn't the starting cycle be same as head and start? Length or okay, starting node. You can find the length of cycle using the approach discussed. Okay. Escape heads of my wishes. Okay. So just because the pointer 1 and pointer 2 met at the same, okay, this is a good one. So you wouldn't know this unless someone gives you a hint or you had like strong mathematical background. So starting pointer and ending pointer, no, slow pointer and fast pointer, if they met, that does not mean that's the beginning of the cycle. It could meet here, it could meet elsewhere, not necessarily. And in this diagram it is meeting at the beginning of the cycle, but that won't be the case always. So which is why we have to find the length of the cycle and then move the fast pointer by k nodes until both of them meet. That's my assumption. Okay, so this is the node. Then calculate cycle length is similar. Current equals to slow, break, you just add cycle. Calculate cycle length. Slow, current equals to slow. Oh, okay, wow. To calculate cycle length, you don't need the fast and slow pointer. You just need the head of the list. Is it the head of the list? You still need to jump fast pointer and then you calculate length of the cycle from the slow pointer. slope point have been incrementing one by one. You can ask the this is weird. Okay, this is pretty involved. Is this an easy question? Okay. I don't feel good. Okay. What's happening here is they've got a couple of functions. First, you find where the 2 pointers, fast and slow pointers meet, and once it met, you calculate the length of the cycle, and then pass that length, and you have to transverse that many times to find the pointer, which doesn't make sense. Why would you want to do that? Okay, I spent too much time on this. Let's move on. This is stuff. Happy number. Happy number makes me sad. Any number will be called a happy number if after repeatedly replacing it with a number equal to the sum of the square of all digits leads up to a number. Okay, so 23 plus 2 plus equals 13, and then if you do that, get 10 and get 1. So yeah, I have to do step 13 leads us back to step 5, and the number becomes equals to 89. This means you never reach 1, therefore it's not a happy number. So here we have to find the cycle. So the cycle link is a problem first and slow, but it specifies. Number, slow, fast. Find square number, slow. Pretty interesting. Excuse me. So here we get the digit, get the number more than 0. Sum. And sum, we take digit, square of the digit, sum it. Remove that number. So if we do this number, okay, so let's try this. What happens? I'm not sure what's happening here, so let's try this number. Let's say 24 and number, okay, number, maybe, where's the number? I think I changed the number. Okay, yeah, so we remove the last number. To remove the last number, we divide it by, what does 24 divided by 10 does? Okay, it removes the last number, so you'll get the previous number. Oh my god, this is okay. To get the first integer, we modulo with 10, and then I'll get the last number here. If you want to get every number, so let's say 1 2 3 4, and I want to remove this last number, we do double slash division. Right, okay, it's pretty interesting. And then you sum them all up, and then you get the number, and you have to do it twice for the fast pointer. If the fast pointer means slow pointer, you know, you're good. This one is middle of the linked list. Just same thing, fast pointer, slow pointer. If fast pointer, have to jump twice the times of a slow pointer, and then once the fast pointer reaches the end, wherever the slow pointer is, that's the middle, right? So fast pointer, slow pointer, it's not enough. Then slow pointer next. Okay, pretty good. Let's move on. Oh, this is pretty fucked up problem. Merging intervals. I hate this. Given a list of intervals, merge all overlapping intervals to produce a list that only mutually exclusive intervals. What the fuck that means? So 1 to 4 and then 2 to 5, these two are overlapping. What the fuck is interlapping? Yeah, so overlapping. And what about this? This does not overlap. So we can probably determine if it's two intervals are overlapping if the last value and the first value of two neighboring intervals are larger. So the last value should be less than the starting value of the next interval. Okay, so first to overlap, we merge them into a single list. So we'll return. Okay, this seems easy, but you can easily get fucked. Okay, so this is 2. So definitely there's an overlap, these two. So we take the smallest one for the start, put it there, and then take the wait, what? 6 to 7. It's not ordered. Is it ordered? It's not ordered. Do we have to order? How can we order this? Okay, so there are a few cases of merging. If do not overlap, some part of B overlaps with A, some parts A fully overlaps B, B fully overlaps A. Okay, so this is fine. Mix of sort the intervals, yeah. Start time to interval to A. Okay, so this is the key. Sort the intervals and then make sure the code. Oh my god, it's so long. Such is it. Okay. Right. Seems doable. Alright, let's move on to the next question. Okay, this is medium already. Given a list of non-overlapping sorted intervals. Sorted, so those are the sort time. Okay. Insert a given interval at the correct position. Okay, this is merge all necessary intervals. Mutually exclusive intervals. Mutually exclusive means non-overlapping, I assume. Few approach, we can just add them first and then go through the entire array. Oh no, we merge, we add wherever that it makes sense, and then look for the neighboring. Yeah, if it's not sorted, we could just simply attend to the array, then let it do the sorting and stuff. When inserting a new interval and sorted list, we need to find the first correct index which can be placed. In other words, we need to skip all the intervals before and start of the new interval so we can iterate through. Once we have found the correct place, we can follow similar approach and set the merge. Okay, skip. As less than interval and intervals dot I is and less than intervals dot. So just keep and add to output all the intervals that come before the new interval. So add all that, merge all the intervals that overlap. Okay, get the current interval, minimum of the current interval, maximum of the end interval. Add them together and append it, and then add all the remaining. This is beautifully written. Intersection. No, I don't have time. Let's move on to something else. Cyclic sort. Alright, I think I should take a break. I'm gonna take a quick break. PRB. I'm back. Okay, cyclic sort. We're given an array containing n objects. This means the object with sequence number 3 was created before the sequence number 4. Try the function is the object in place the creation sequence number on without any extra space. For simply, let's assume we are passing an integer numbers sequence numbers. Each number can actually be an object, though each number is actually an object. And objects, each object is created when created or assigned to a unique number from 1 to n based on the creation sequence. This means the object with 3 was created just before I write the function sort the place without any extra space. For simplicity, let's assume that we are passed an integer any containing only a sequence number. We have to sort in place. How the fuck we do that? That's a good point. So since we know all the numbers are supposed to be the right place, what you can do is, okay, once you read 3, look at the position 3, and then you swap, and then look at the new place. 5 is at the wrong place, and then you swap with the 5th place. Where's 5th? And then you move to the 2nd, and then look at this and move to 1. Done. Okay, start and then a correct place, and then you find 6 and then 6 you swap with 5, and then 5 you swap with this, and once it's a correct place, but then you need to move the start pointer to the next, and then you can okay, yeah, so we have to increase the pointer. Yeah, pretty interesting stuff. While I'll is less than nums j equals to total current number. I would expect it. Okay, this is a swap I and j. Swap I and j. You take the value -1 to 0 index, and then check if these two numbers are the same. Why you have to check this? Okay, so this is gonna loop itself. That's interesting. It's clever. You don't increment unless these two numbers are at the correct places. The numbers that you swap are the correct places. You don't. This is an optimized code. I don't know, when you start writing code for the first time, you come to this optimized code. You probably have 2 loops, while loops. This code is optimized. Okay, this is cyclic sort apparently. Pretty interesting pattern though. Finding the missing number given an array and containing ballistic. How we can do this? So, given a number, in this case the missing array is 2. Okay. Unsorted. Simple. We go by each number. check. Okay, cyclists are placed number on correct index. Once you have every number in correct place, you can iterate the index, find and does not have the correct. This problem number should be equals to its index. Since the array will have n numbers, which means the array indices. Yeah, it's similar to that one, but it's except for that it's the range are different, and then be less than n numbers, which means that the integers will range from 0 to n minus 1. You ignore the number n. Okay, so this is catching the edge cases. So zero to n. Okay, this is find all missing numbers. A similar find missing numbers for remaining duplicates, missing numbers, no duplicates. Okay, it doesn't line for it. However, we'll follow similar approach to discuss and find place the number. Once we are done with the cyclic sort, we will iterate the array to find all indices. So we sort. I don't understand, like, I think it's just 0 to n, but not including n, right? The array will only range from 0 to n because one number is missing. Therefore, we'll ignore the number n as we can't place it in the array. So we had additional. So this is probably something I'll definitely miss. And okay. Okay, this seems like does not have that problem because it starts from 1. J minus 1, you just swap and then increment. Okay, alright, let's move on. I think let's move on. We sort it, and once we sorted it, whichever number that is not is the correct position, that's the missing number. Does this account for duplicates? It won't keep infinitely swapping because we just increment it. Okay, we are given an unsorted array containing find the duplicate number without using any extra space. Given an unordered array containing n plus 1 numbers. What is n? N is range from 1 to n. So n is 4. The range n is 4, but it contains n plus 1 because 1 is duplicate. But yeah, here's 3 duplicates. The two numbers are the same. We found the duplicate. Let's swapping the two numbers, and then the two numbers are the same. Previously, we will just keep on going. Previously, would have just keep on going. If we find if the yeah, I don't know. Going on, given the number of sort, I don't understand what's going on. I kind of get the general concept, but yeah, I kind of get the general concept, and that's it. Implementing it would take me to trace through each example, and that would take a lot of time. Okay. Okay, I forget this. This is a linked list again. I hate linked lists. I had a lot of things. Given the head of linked list, reverse the linked list, write a function. Okay, this is supposed to be easy, but previous equals to null, current, and then what do? You change current, point it to previous, then move the current to the next. Okay, you copy the current's next value to temp, and then move current's next value to previous. Yeah, right. And then move the previous to right. Current's next value. Yeah. Let's keep on doing it. It sounds easy. Previous, current, next. 3 pointers here. Next had none. Well, current is not none. Next equals to current.next. Current.next set to previous, and previous was none, and then previous equals to current. Next node, point the previous node to the current node, yes. Move the current node to the next node. So we just move that pointers to the next part, and yeah, it's pretty straightforward. Reverse the sublist. Given the head of linked list and two position P, Q, reverse the position from P to Q. So we have to traverse all the way until P and then keep reversing, and then we have to chop the string. Skip first P minus 1 parts to reach node P. Remember the node position at P minus 1 can be used later to subplace. Next, reverse from P to Q using the same proportion, then connect P minus 1, P minus, okay, reverse subplace. Holy shit. Just transfers, and then we are interested in the first three parts of the linked list before index P, part between P and Q, and part in Q. After reversing the linked list, we keep an integer. So what's the distance, how many times you have to do that, and we do that many times, the reversing part. And once it's done, it's not known, this is medium, reverse K, oh my K, while true if current is not on break. Okay, makes sense. All right, let's move on to next. Okay, here comes the trees. Let's go. How's the live stream coming so far? I hope no one is watching this, and I'm going to delist this if anyone's watching. Oh, there's been already 3 views and people left, and no one's watching it right now. Not working connection. Who's AC Valala? Hello, hi. Sorry, I was not paying attention to the chat. Yep. On leave today, gents. By the way, who's AC Valhalla? I know it's a game reference. Why so anonymous? Hi, stupido man. Thanks for dropping by. And Rengoy, am I pronouncing your name right? You sent a message but then you retracted it. I don't bite, it's okay. Yeah, streamer not reading chat because streamer is on a tight schedule. Okay, so let's move on. This is a binary tree problem. Given a binary tree, populate an array to represent level bar ever. This is a pretty interesting problem. You should populate the values of all nodes at each level from left to right. Since we first transfer all the nodes, can use a queue to efficiently traverse BFS fashion. Here are steps to algorithms. So I start. Okay, you can use a queue. Yeah, yes, use a queue for BFS, baby. BFS. Oh my god. Start by pushing your root node to the queue. Keep iterating until the queue is empty. Yep. Each iteration, the first count of elements in the queue, call it level size. With all the many nodes, you'll have these many nodes in the current level. I hope whoever turned for that live stream had a good time. Mostly I was mumbling. It was not intended for a public audience, but I'm just doing it so that I get a little bit of confidence. Right, okay, so we left these many nodes in the current level. So next, move to remove level side nodes from the queue, push the value in an array to represent the current level. After removing each node from the queue, insert both children to each iteration. First count the number of elements in the queue. Level size. After removing each node from the queue, insert both of his children to the queue. Okay. If the queue is not empty, repeat from step 3 to the next level. So this level size equals to 1. Push that thing. And then queue becomes empty. Pop that thing. Pop that thing. Pop those two numbers, and for each number add the children's. The level size equals to 3. Move the 3 elements output or representing third level. Okay, the code is from collections import dequeue.append root level size. Where's level size? While queue level size is line of queue. Current level. So you just append the current level to the array. For level size, queue pop left. Okay, I think I need to take notes of this. Okay, so from collections, so BFS dismiss BFS, we need to take note in from collections import dequeue and to append, so queue goes to dequeue. So these are like cheat codes that you probably need later. Then queue can append X, and then queue pop left to remove the item. I think you can do peek as well, if I'm not mistaken. Okay, so for level size is the size of the queue before entering the loop. Pop the queue, current node, and current level. So current level, append current node to value, current, and then if the value exists, you just append to the node, then it will get current level. So you do it. Yeah, this is beautiful. It seems easy, but when you want to do it in a high stake environment, I would call it that. You need to keep that in mind, like how do you do that. So we need to keep just so the size of the level, and size of the level will be the size of the queue, right? BFS using binary tree, and then you can just use left right pointers, add it to the current level output. All right, moving on. Given a binary tree, populate to array to represent level by level transversal in reverse order. That lowest level comes first. You should populate the values of all nodes in each level from left to right. You should populate all nodes from each level left to right in separate subarrays. Similar, you can follow up similar, but the only difference will be instead of appending the current 10, we will append to the current level beginning of the result list. So use result. Okay, so another method is append queue.append left. Append is appending to right, I think. Let's check it. Python dq append. Append. Okay, so this is good. Append left to the left. Insert the element with specific index. Extend used to insert multiple values at the same time. Takes list of values in argument. Extend left. Okay, this is a good cheat sheet. Panel item deletion, pop left, remove the first occurrence of the mentioned value. Rotate the queue n number of times. Reverse the order of the queue. Extend, insert, append left, append, pop. So pop, what does pop? Pop removes the stuff on the right. This removes stuff on the left. Okay. Cool. I'm just looking at the chat and okay, never mind. It's too late for that. Let's keep moving. Zigzag transversal. All right. I think I've got like 20 more minutes. Okay, it's okay. Notice the first level from left to right, then right to left for the next level, and keep alternating between the same. So similar, but we just had a boolean flag whether to append left or append right, and be done. Binary tree level averages. Okay, that makes sense. For the level averages. Minimum depth of a binary tree. What does that mean? Minimum depth of a binary tree. Minimum depth is the number of trees, number of nodes along the shortest path from the root to the nearest leaf of a node. Oh, nearest to the leaf, so 1, 3, 12, 7. That's the nearest. This is this is also can be the nearest. Fine. So how can we find the first leaf node? As soon as we find the first leaf node, that level represents the minimum depth of the tree. And then if the current node is left and right, that's the minimum depth of the tree. Okay, why is that true? Why does that hold true? Okay, so there's no left and right. For this level there's no left and right, and that's the minimum. For this level, when you hit here, there's no left and right, so that's the leaf, so that's the minimum. I only need to keep minimum depth 3 plus 1. Okay. Well, Q gets popped every iteration, so eventually it has to stop. Level order. What the fuck is level? Given a binary tree, find the level order successor of given node in the tree. The level order successor is a node that appears right after given the node level order of reference. Given a binary tree and node, find the level ordered successor of the given node in the tree. Oh. Given the binary tree, find level order successor of given node into this tree. The level order successor node appears right. Okay, so here this is the level order, so it comes here. 9. Okay, this is Oh my god, that's so simple. We'll we'll keep inserting the child nodes to the queue, but as soon as we find the new queue node that we're looking for, we return if we return the first item in the queue, and none if it's nothing. That it's pretty interesting. Love it. Given a binary tree, connect each node with its level order successor. I think I don't need it for now. My ears are pretty huge, and it was a mistake to get over the ear headphones. It's not compatible with my satellite dish ears. So the last node of each level should point to a null node. Okay, let's see. Okay, that makes sense. So what we're doing here basically is same as before, but if there's a previous node, we change the previous node's next pointer to the current node, and then we keep on doing that. And this will get reset every time that when we change the level size changes, it gets reset. This is a really brilliant solution. Okay, now let's move on to tree depth. I hate this. Okay, given a binary tree and the number s, find if the tree is a path from root to leaf such that sum of yeah, no. Find the tree as path from root to leaf such that sum of all the nodes values of path equal to s equals to 10, sum equals to 10. Is that a path? Yes, that's a path. Okay. 23, there's a path, there's no path. So this pattern is different. Here we're not looking for the okay, maybe I should copy this code somewhere. Okay, well, q equals to q, well, q append root, and then well, q and then level size equals to len of q, and for I in range level size node, you don't even need I, swap that current node to whatever you want, and then append q.append and dot left q dot append and dot right. That's basically the code. From collection put the q append the root, appending to right, and then well q get a size, and for each size you pop the item from the queue and then you append a node. If not none, only append it if not none. So this is for brevity. This is just for brevity, so that the high level code looks clean. Okay, so this is the pseudo code for BFS. You can use this. What about if it's a DFS? What we can do, okay, so to recursively transfer a binary tree in DFS fashion, we start from the root, and at every step we make two recursive calls, one on the left or one for the right child. Here are the steps for binary tree to some path problem. If current node is not a leaf node, do two things. Separate the value of current node from the given sum. Make two recursive call both children of the current node with new number calculated from. So it's just dynamic programming. And we break down the problem and pass it down to the level below. So here's this 23 and this at the root node, you pass down, you minus this value from the sum, pass down that 11 to this value, and then this will call the child, and then it'll call the child. It's not left 9, and then this is the child node, return false, and then the right child is null. Then we go back, we go back all the way back up. I'm mumbling. No. Why am I mumbling? We just crossed 1 minute, 1.5 hour mark. Keep on doing that until, so this is basically tree node has paths. Okay, so if root is non, return false. and root dot left minus root dot well, or this is amazing. Okay, let's see if we can find DFS transfer. Searching for a node in the binary tree whose value equals to target. So if root is none, return none. If root is target, value equals to. And if left, DFS target. I'm quite worried. I go silent for long periods of time. I should not be doing that. Whatever that's going in my mind, I'm supposed to scream that out so that someone else could hear what I'm thinking and help me out, ideally. But I'm not doing that. I'm just keeping my thoughts to myself. And when I'm talking, I can't think when I'm talking, or and I'm more productive when I'm not talking, when I'm thinking. Right? I get more thinking done if I don't talk. So if root is known, return false. So it's not equal to sum, and it's not known. Wait, node dot value equals to sum. Okay, makes sense. I was thinking like maybe root value minus sum equals to 0, so it's the same thing. Same thing. It's a good thing. It's a good thing. All right. Going back to our notes. How do we print DFS? So we are trying to think about how we can print all parts. all paths from source to target. Graph list. Kick off the backtracking start from source node 0 path. Okay, DQ. This is syntax error. Is it a syntax error? Current node equals to target node. Each node visit if current node lived at current path if not changes. I'm trying to figure out like a generic algorithm for depth first search. Yeah, screw this. It's taking way too long. The only thing I'm trying to do is just find the DFS function. So def DFS, we get a node, and then we want to print DFS node dot left DFS node dot right. Maybe I should search for DFS print in order. I mean, these guys are fucking dumb. What kind of code is this? So we need visited. So DFS for visited. Anyway, forget it. I'm wasting too much time. All parts for some. Okay, this may be what I was looking for. Okay, find parts. Add to current path, all paths add. If it's add current path. Node. If return if node.left is none and node.right is none. That's the end node. So paths dot current path else you have to call recursively DFS recursive node dot left current path DFS recursive node dot right current path. So the current path, in the current path we need to add the current node value. Current path, add the current node value, and if the node is a leaf node, then append the path and you call it off. If it's not the leaf node, you can call the left node and ask it to return at that path, and then if it's not, just keep on doing. And if it's not, it's not. You can actually check it here, but whatever. This is the main logic, I suppose. And how would you call this function? Is DFS recursive node. The current path is empty. This is how we call it, and then return paths. I think this is how it's been done. It should be done. I'm not sure if that's the case. So yeah. Does that make sense? It's a good thing that no one's watching this, because it's just I'm just quiet most of the time. Okay, let's move on. Okay, sum of parts. Given a binary tree where each node can only have one digit, each root will represent a number. Each root to leaf path will represent a number. Find the total sum of all. Find the total sum of all. So okay, so this is exactly what I was looking. Current node 0. If not, we're just adding the sum here. We're not keeping track of the sum so far. So and then we pass down the sum, and then I think I'm jumping too fast. Okay, 117, 192. Okay, so this is a bit more involved than I thought. So current value times by that, and then add this number. So okay, that makes sense. Add the sum, part sum so far. If written, if it's a leaf node, you return the sum, and we okay. So from the root node, we sum the left node and the right node. Sum from left node and right node, and then it recursively does the addition. Perfect. Part with given sequence. Interesting. Given a binary tree in sequence of number 5, is the sequence present in root to leaf path in a given tree. This problem follows binary tree sum part. TDS approach additionally track the given sequence will be matched. Okay. So find path if not root, if not node is none. False. Sequence path find recursive path. Why do you need a sequence index? Sequence. Oh, okay. Wow. Sequence index start from 0. And current node is none. Return false. Sequence length if sequence index is more than or equals to. Okay, so this is edge case. This is a terminal case. It's not because this, and then it's not none. Okay. Okay, so so it'll just return, most of them will return false, and then if there's one or that's true, this is an edge case, and this is this, and it goes out of bound, we return false, saying there's nothing, or if the value is not the same, we'll terminate early. We don't have to go all the way down and then return false. So we'll, if the sequence and index not matching up, we just return false, and each one of these have 2 copies of it. Okay, this is a pretty interesting problem. Count parts for a sum. Is it medium? It's medium. Find all parts in trees such as sum of all nodes of values each path equals to s. Please note that paths can start or end at any node, but all paths must follow direction from path to child. Okay, I'm not worried about it. I'm actually worried about it. I'm more worried about problems where you need to count diameter of a tree, or like the left face of a tree. That kind of problems can get tricky. Maybe I should end this stream and go crazy. Maybe not. Let's just stay until the very end, which is probably 40 minutes, 30 minutes from now, I guess. I'll terminate I'll stop the stream in 30 minutes. But we are only, oh my god. Okay, I'm gonna take a break. Very quick break. I'm back. Okay, so we have got 30 more minutes. Actually, no, about 25 minutes. Let's go to the next pattern. Designing a class to calculate the median number of string. Design a class to calculate median number of a number string, median of a number string. So following two methods: insert and find median. Inserting will take a sorted list. Inserting a number in a sorted list will take a times number of there are numbers in this insertion or something insertion sort. Assume x is the median of the list. This means the first of the number will be smaller than or equals to x, second of the list. This will lead to approach where we can divide that list to half. One half to store all the numbers smaller, and another half to store all the numbers larger. If total number of elements is even, the number will be average of two numbers. Best of the gesture that comes to mind when find smallest and largest number on list is a heap. Let's see how we can use a heap to find better algorithm. To start first of number by maxing. We should use max heap if you're interested in knowing the largest number in the first half. And we store min heap when the smallest number. Inserting number in heap will take log n, which is better than brute force approach. At any time, median of the current list number can be calculated for. At any time, the median of current list of numbers can be calculated from top to lowest. You can insert number in the max heap if the number is smaller at top than top largest number of the heap. If the count of the number of elements is odd, let's decide to have more numbers in max heap. If the count numbers is odd, let's decide to have more numbers in max heap than min heap. So add 3 and okay, as 1 is smaller than 3, let's insert in the max heap. Now we have two elements in the max heap and no elements. So let's take the largest element from the max heap and insert into the min heap to balance the. Oh wow, this is interesting. So, so as we have the even number of the median value should be the top of both the heaps. Okay, if insert number is greater than top both elements of the max heap, we can insert in the min heap. After insertion, total number will be odd. As we decided to have more numbers mix heap, you can take the top smallest number min heap and insert the max heap. As 5 is greater than element of max heap, we insert into min heap. Okay, find the median. Okay, sure. No, sliding window median. Next, pattern subsets. Given us distinct, find all of his distinct subsets. To generate all subsets of a given set, we can use the breadth first approach. We can start with any empty set, iterate through all numbers one by one, add them to existing. Take the example 2 mentioned above through each set. Well, this is a combination subsets problem. Okay, subsets, add empty subset, and then for current number for each element, subsets, total number of subsets. Okay, so whatever subsets that we have already that many times, we copy each of the subsets and append the new value. This is brilliant code. I'm running out of time. Okay. Given a set of numbers that might contain duplicates, file all its distinct subsets. Distinct subsets. Okay. Since given this, because we force import subsets, we end up with duplicate subset which is not suitable. To handle this, we will do two extra things. Sort number given set to ensure that all duplicate numbers are next to each other. Sure. Follow PFS, but whenever they are about to process a duplicate, instead of adding all the we only add it to the but when we are about to process a duplicate, instead of adding the current number to all existing subsets, only add it to the subsets which were created in the previous step. Okay, let's take example. Add the first, add the second number. The next number is duplicate. If we add it to existing subset, we will get okay, that's correct. We got two duplicate subsets. Guys only need add to add. To handle this, instead of adding all existing, we only add it to the new subset which are created. Step. Only added to the new subsets. Okay, so we just add it to the last subset. That makes sense. So this is we only add it to this one, but not everything else. Okay, so as a duplicate if okay, all right, this is cool. We just change the start index and then you just basically add it to 1. Okay. Permutations. Given a set of distinct numbers, find all of all its permutations. For example, 3, 1, 2, 3 has the following 6 permutations. This form subsets pattern breadth first approach. However, unlike subsets, every permutation contains all numbers. So make sure to generate all permutation following BFS or branches of one at a time. If a given set is empty and we have only empty permutation, so let's add the first element. Let's add the second element. Let's analyze permutation test type. How we can generate. If we look closely, we'll realize that when we add number or new number, we take each permutation of the previous step. If permutation of the previous step, we add number every position to new permutation, for example. Okay, so okay, this is interesting. Moving to the next one. Given the sorted array of numbers, if given a number key, though we know the array sorted, we don't know if the sorted ascending or descending array, should assume the descending have duplicates. Though we know the array is sorted, so you can determine if the large is smaller than that, or smaller than. Okay. I'm gonna pause sharing my screen for a bit and look at my Colab to see if I've encountered similar problems before. Actually, I think I'll just end the stream here for now. It's going to be an interesting evening, and thanks for tuning in. Bye.